Today, we're going to tackle a question that sounds almost childishly simple, but it's one that stumped humanity's greatest minds for over 2,000 years. The question is, why do things move? And let me tell you, the journey to the real answer completely rewrote the rules of reality itself. I mean, it seems obvious, doesn't it? But it's not. The story of how we figured this out is an absolutely incredible tale of observation, pure imagination, and the total overthrow of what we call common sense. All right, so let's just dive right in. To really get a handle on the laws of motion, we first have to understand the brilliant but deeply flawed idea that pretty much dominated all of human thought for 2 whole millennia. So our story kicks off way back in ancient Greece with the philosopher Aristotle. His ideas about motion were so intuitive, so logical, they just seemed to perfectly explain the world that we all see and interact with every single day. So here was Aristotle's core idea. The natural state for anything, for any object, is to be at rest. It just wants to sit still. So to make something move and to keep it moving, you have to constantly push or pull on it. You apply a force. The second you stop pushing, it stops moving. Simple as that. And you can see why this idea was so powerful, right? It just perfectly matches everything we experience. You pull a little toy car, it moves. You let go of the string, it stops. You kick a football, it flies for a bit, but then it rolls to a stop. It just feels right. And that powerful appeal to our common sense is exactly why this idea stuck around for centuries. But here's the thing. This common sense view, as logical as it seems, has a huge, massive flaw. It's completely overlooking a hidden and ever-present force that is always working against every single moving thing on Earth. And that's the key. That's the whole secret. Friction. The toy car doesn't stop because its natural state is rest. Nope. It stops because the invisible force of friction from the floor is actively dragging it to a halt. The push you give it isn't creating motion. It's constantly fighting against friction. So for 2,000 years, this one invisible force, friction, completely clouded our understanding of how the universe works. It wasn't until the 17th century that an Italian scientist, Galileo Galilei, made this incredible intellectual leap that changed absolutely everything. Now, obviously, he couldn't just build a frictionless world, so he used something even more powerful: his imagination. He ran a thought experiment. By just imagining an idealized, perfect scenario, he could mentally erase the distracting effects of friction and see the true laws of nature hiding underneath. Okay, so picture this. Galileo imagined a ball rolling down a ramp. It rolls down one side and then up another, and he noticed it always tries to get back to the same height it started from. So he thought, what happens if you make the second ramp less steep? Well, the ball has to travel a lot farther to reach that same height. And then came the big question. What if you make that second ramp perfectly, completely flat? Well, to try and reach its original height, the ball would just have to roll forever. And that was it. That was the revolutionary discovery. In a world without friction, an object in motion stays in motion. And this is so important. The crucial point here is that motion is not the opposite of being at rest. Both standing completely still and moving at a steady, constant speed are totally natural states for an object. The thing that requires a force isn't motion itself, but a change in motion, what we call an acceleration. This brings us, of course, to Sir Isaac Newton. He took Galileo's absolutely game-changing idea. He refined it, polished it, and made it the cornerstone of his 3 legendary laws of motion. We call this the law of inertia. And inertia is really just a fancy word for an object's laziness. It's built-in resistance to any change in its state of motion. The more massive an object is, the more inertia it has, which just means the harder it is to get it to speed up, slow down, or turn. So the core idea is actually pretty simple. Whether you've got a book just sitting on a table or a spaceship coasting through the vacuum of deep space, if its velocity isn't changing, the total net force on it is 0. That's it. Being at rest and moving at a constant speed are basically the same thing from a physics perspective. You feel inertia all the time, especially in a vehicle. You know that feeling when the bus suddenly lurches forward? You feel like you're thrown backward? But you're not. The bus is moving forward, and your body, because of its inertia, is just trying to stay put. And when the bus slams on the brakes, your body wants to keep moving forward. It's not some mysterious force pushing you. It's just your own body's resistance to change. Okay, so we've established that a 0 net force means no change in motion. But What happens when the net force is not zero? Well, that brings us right to Newton's second law. Now, to really get the second law, we first need this idea of momentum. The easiest way to think about it is as a quantity of motion. It's a combination of both mass and velocity. So, a really heavy truck moving pretty slowly can have the same momentum as a tiny, lightweight bullet moving incredibly fast. Newton's great insight was that a force doesn't just cause motion in a vague way. No, it's very specific. A force causes a change in an object's momentum. The bigger the force you apply, the faster that momentum changes. And since, for most objects, the mass stays the same, a change in momentum is really just its mass times a change in velocity. And a change in velocity over time is what we call acceleration. This brings us to probably the most famous equation in all of physics. Force equals mass times acceleration, F equals ma. This is the engine of classical mechanics. It lets us calculate and predict the motion of pretty much anything. So Newton's first two laws are great for describing what happens to a single object. But his third and final law reveals this really deep and profound truth about how forces actually work in our universe. And the secret is they never, ever act alone. You've probably heard this a million times, but it's also one of the most misunderstood phrases in all of science. What it really means is that forces are always interactions between two different objects. They always come in pairs. And this is the part that trips everyone up. The key is that the action and reaction forces act on different things. So when you push on a wall, that's the action. The wall pushes back on you with an equal and opposite force. That's the reaction. And those two forces can't possibly cancel each other out because one force is acting on the wall and the other one is acting on you. It's actually this interaction that allows anything to move in the first place. So there you have it. What an incredible journey, right? We went from an intuitive, common-sense idea that held us back for 2,000 years to Galileo's amazing thought experiment, all the way to Newton's 3 simple, elegant, powerful laws that literally govern everything, from a thrown baseball to the orbits of entire galaxies. And that leaves us with one final thought to chew on, a little puzzle. The answer lies in combining all 3 of Newton's laws. It's the perfect test of this powerful new way of seeing the world that we've just explored.